In this video, we will be talking about electric current in intrinsic semiconductor. As we know that intrinsic semiconductors are pure semiconductors, and the current in these semiconductors is both due to the electrons and due to the holes. And we understand that the holes are the positively charged vacancies that are caused by the movement of electrons. So here we have a bipolar current that flows through this semiconducting material. Now, if I go with the simplistic way, suppose we have a semiconductor, okay, and this semiconductor has the length equal to L. It has area of cross section equal to A, and it has the conduction both due to the electrons and holes. So if I connect this thing with an external source of battery, say it's like this, okay. So what's going to happen here is you will have holes drifted in this direction, and you will have electrons drifted in this direction. All right. So so there will be the moment of you are developing a potential difference across the ends of this semiconductor, and there is flow of the electrons and the flow of the holes. Now, the movement of these two equal and opposite charges, they basically constitute an electric current in the same direction. The point is in the same direction. So, therefore, the total current in the semiconductor is the sum of electric current due to the flow of electrons and the electric current due to the flow of holes. So if I have to talk about the overall magnitude of current, so that if that is I, this I must be equal to the magnitude of current due to electrons, then magnitude of current due to holes. Now, the point is that I is the current due to the electrons, and IH is the current due to the holes. Now, if we rightly remember the relation between current and drift velocity, we have I equal to E N A V D. Here, E is the charge of the electron, N is the number density of electrons, A is the area of cross section, and Vd is the drift velocity. And we better know that this drift velocity is E tau by m, where this tau is the relaxation time. Now that's not the point here. The point here is that if I have electrons here, so for electrons I will have current equal to E Ne. So Ne will refer here to number density of electrons. A is same, and V E, instead of Vd we will use here Ve. For Ve is the drift velocity of electrons. And in the similar sense, I can write down the equation for current due to the holes. That will be E now NH AVH. So we can understand here that this VH is the same drift velocity, but it is the drift velocity of holes. So if we proceed from here, we can see that that the net current that flows in this piece of semiconductor, that will be I equal to E N E A V E plus E N H A V H. So this should be the case here. And if I have I can see that that E is same, the magnitude of charge is same, and the area of cross section is same. So I can have NEVE plus NHVH. So this equation is going to give me the magnitude of current that's flowing through this semiconducting material, which is basically an intrinsic semiconductor in which the carrier concentration of electrons is equal to that of the carrier concentration of holes. And this electric current in a semiconductor is due to the flow of electrons and holes. And if we look at the metals, in case of metals, the current is only by virtue of the motion of what I call as electrons. Now, if we proceed from here, we can have this current divide by A equal to NEVE plus NHVH. Now, this is current by area. This I by A, we call it current density, and it is symbolized as J. And we can use this J here, and J must be E times NEVE plus NHVH. We also know that this J is equal to sigma E. This is Ohm's law, right? So if I use for J here sigma E, I will have E times NEVE plus NHVH. So the conductivity, which I'm interested to have an expression for conductivity, that conductivity will be E by E times NEVE plus NHVH. I think up to this, the things are clear, that we are calculating the conductivity of these intrinsic semiconductor materials. Now, from here, we can think of this electric field. We can take this electric field inside, and we can have sigma equal to E times NEVE by E plus NHVH by E. Now this mathematical ratio between the drift velocity and electric field, we call this as the mobility. So this VE by E is nothing but mobility. Now, mobility gives us basically the measure of the ease with which a charged particle can move inside the material. So, for electrons, I would like to write it as mu E, and for holes, this mobility is mu H. So, in all, I have the conductivity here, and this conductivity is E times NE mu E plus NH mu H. So this equation is going to give us the measure of the conductivity of these materials. Now, if in case of intrinsic semiconductors, if I choose, because this is an intrinsic semiconductor, I can have this Ne equal to Nh. Let me put this equal to as Ni. So in that case, sigma will be E times Ni times mu E plus mu H. And we can see here this if we go back to the point of mobility, this, since we understand that the uh, drift velocity depends on the on the on the mass of the current carriers. So if we rightly go back there, drift velocity is, it is E tau by m. So it has a dependence on the on the mass of the charged particle. We can immediately talk about this drift velocity, the magnitude of drift velocity for electron. It should be greater than that of the magnitude of drift velocity of holes. That should be the case because electron is lighter than hole. Therefore, if this is the case, therefore I can say that mu h, the mobility of holes, should be what should I call it? It should be greater than that of mobility of electrons. And so this way, what we have done, we have seen the conductivity of these semiconductor devices, and the case is here that we have treated an intrinsic semiconductor, a pure semiconductor. We have applied the potential difference across it and calculated certain parameters. But to the essence of its excellence in the field of technology, these semiconductors do not have technological importance because they cannot provide us the right amount, the right magnitude of currents that we are interested in, and we are able to use in devices. So so in order to make these intrinsic semiconductors technologically important, uh, uh, what we do is we try to change the properties of these intrinsic semiconductors by using the concept of doping. So what is doping? What we are trying to do is we dope the parent material with some doping agents, depending that what kind of charge carriers you want in the semiconductor. And when we dope these materials, we are able to manipulate the conductivity of these semiconductors. The doped semiconductors that we achieve here, we call those semiconductors as extrinsic semiconductors. So in the next video, we will have some look at the extrinsic semiconductor materials.